Okay, Muthan, do you want to get started?
Sure, yeah, I can get started. Let me share my screen then. Okay, so let's see, we were doing Pixel CNN. So I think today I want to wrap up the homework and the collab. And so we can go through
Actually,
it.
we've scheduled 2 more sessions for collab. So I think collab is like a lot more. So we can take our time with at least finishing homework would be a good objective today.
Okay.
On the Pixel CNN variants today.
Yeah. So, okay, we can. The collab one is all the models are pre-trained, so it's very hard to see what's going on. But yeah, we can have discussion at the end and see how we can do more on that.
Okay, sounds good.
But what I can do is I'll go over the homework, the Pixel CNN part, and then go over the collab so we have a good idea and we can plan out how to go forward.
Okay, sounds good.
Okay, so we were doing Pixel CNNs last time. So we've done this one, Pixel CNN. So we've done made. So the idea is the same. Pretty much the same as before, right? So you have a mask, and then you apply the mask to your weights to zero out in the convolution layer. There was one slight confusion last time, my confusion, but so let me clarify it. So just to see what the masks look like. So if I look at the mask, they all look like this. So there's it's 0 here, but it's three rows of all ones and 3 columns of all ones here. And then it does say it's 64 by 1 by 7 by 7. So there's 64 of these, and all of these are exactly the same. So if we look at this, this is what they call type A. It's not explicitly said here, but it's either type B or type A, and only the difference is this one. This pixel is a 0 or 1. In type A, it's 0, and in type B, it's 1. Right now, this is the first layer, so the type A is only used in the first layer because so here's the complication, or here's the subtlety. Here, when we look at this, so let me go to the console. Okay, we're not there yet. So if we look at this CNN, we'll see that the right here, the kernel size is 7. Right, so 7 by 7, and padding is 3. So can you imagine for the first pixel, this 3 is padding, and this is these 3 are padding. So if we were looking at our first actual pixel, so all 3 would be padding, all 3 would be padding, and this would be our first pixel. So the mask first zeroes it out. So we can't use that first pixel. And then on the second layer, but does that make sense why it's shaped like this? The kernel size here given is 7, so it's a 7 by 7 matrix. So we have the kernel size and the mask must have the same shape, because that's the one we slide along in the CNN. But we start with 3 here, 3 columns and 3 rows of ones, and then 3 by 3 is the first starting point because we have padding of 3. So all of this is zeroed out in the actually we take the picture and we pad it with 3 by 3 all around. And then the first filter that we do and the first mask has the zeroed out here. So that's why the mask looks like this. So let me go to the type B mask. So the I think I put it down here somewhere. So this is the this is for both of them, but this is essentially what it looks like. We have the input, and it gets converted into input is 1 by no, not this one. Sorry, it's not this one. I can go to it right after this. So let's look at the mask here, the second set of mask, which is of type B, and we notice that this is 1, but this is a different layer. So the it's going from 64 to 64. So just to make that a little bit more clear, I can show the architecture. So our input here, it's same as before, which is 1 by 20 by 20, 20 by 20 picture of 0 or 1 grace binary image. So it takes batch size 1 2020 and converts it into 64 2020, and then it maintains it throughout. So each one, each mask, there's 64 masks there. And then since each of these has kernel size 7 and padding is 3, all the masks match up because that's the only mask you need. You have 3 by 3 padding, and so the first pixel is in position 3 by 3. So all of the rest it can be padded up. Does that make sense why the mask is that way? Okay, I can we can look at the mask again. Right, so this is type A. So type A means that it's the bottom layer, the first layer. So in the console, oh, the console it's already gone. I should have copied it. Let me do that right now. So we have a copy of the architecture. So it goes from input and then goes into 20. So 1 by 20 by 20 turns into 64 by 20 by 20. And then there's the layer normalization, ReLU, and then another mask. So for each of the convolution layer, there's a kernel size of 7 by 7. So the kernel size is the same size as the mask. So the kernel size is imposed on the picture. We multiply everything, condense into a number, and then it's output as another number here, because and then there's 64 of them. So the size goes from 1 by 20 by 20 into 64 by 20 by 20. And so the kernel size is 7 by 7. The padding is 3 by 3. So the image 20 by 20 has a 3 by 3 padding. And so if you look at the mask again, so the first 3 rows and the first 3 columns are just padding. And so the actual image starts here. And so this is our mask. So it's zeroed out. So the first iteration cannot use the 0th position. So if all the input is zeroed out, and then the mask moves 1 step to the right, as with convolution. That's how convolutions work. Yep. And there's 64 of them. They're all the same. So I think this is just, this is done to keep all these masks around for part 3 of the question. I think just one mask would have been sufficient. They're all the same because they're all doing the same thing. Even though there's 64 of them, they're all exactly the same. But if we, yeah, the convolution video, I think, yep, right here. So each of this is a 7 by 7, and then we have a padding of 3 by 3, and it slowly slides over. And only this part is masked out as we have shown, so that it cannot see the future of the image. And then it slowly slides across, and then it creates the next layer. And then the next layer has another mask, similar 7 by 7, and it slowly slides and makes the next layer. Except in our case, it's all the same size. So in our case, it's always 64 by 20 by 20 until the last one, which is 2 by 20 by 20. And I think that's how pixel CNN works. Everything else is exactly same as made. So the forward is just yeah, pixel CNN. Everything is the same. The loss is the same. Just cross entropy. Sample is just the same. So you go for the size of the yep, the size of the image, and then the number of channels, which in our case is 1. So it doesn't matter, but because it's binary image. But just like with made last time, what it does is goes through each pixel, and then goes through each channel, asks the self.sample. So it says run this through the forward, do a forward pass on this, do a softmax, so you have probabilities, and then just do binomial coin toss between the values given, and then we have the and then okay, and then after it runs, we'll have the
one question on the
sure.
KRC. Sorry, it seems to be 5 dimensions, right? What are the? I mean, one is batch size, and then KRC. What's the 5th dimension? Or am I?
On which one? This one?
No, where you had the code where it showed the looping through.
Oh, okay.
They are and the C.
Sample. Okay. This one, right? This is the X dimension. This is the Y dimension. So we're going. Oh, I'm sorry. This is the first is the Y dimension, and then the second one is going this way. It's probably in matrix form. The third one is the number of channels. This is for when we deal with color images.
Yeah, for future. But the one below that seems to say 5 axes, right? Or
oh, this one. So KRC, this is samples is the N is also there, the number of samples. So we're making 100 pictures, but we're making all of them at the same time.
Okay. So it's then, but isn't there, there's no batch size involved? What's the?
Oh, here, this is, it asks for, oops, yeah, okay, I see. So you ask for how many samples do you want to make? And that's
right. So that would be 100. So
100.
There'd be one more. So 100 samples of KRC, but then what's the 5th dimension that's also there, because there are 2 colon commas, right?
Okay. One is the number of samples. I think the other one is just extra dimension. It's just for the binary image. So yep.
So that would be the 2 values, but wouldn't that come?
Can see input shape. Yeah, I think the input shape is yeah, the channels would probably do that. So let's see what it is. Yeah, the input shape is 1 by 20 by 20. So samples is 100 by 1 by 20 by 20.
So it's that one that is there and gets squeezed out later, or because when he does later on the dot multinomial, that goes away. But here there seems to be one more.
See, this only seems to be 4 dimensions. Samples only has 4 dimensions. So
right, but that's because he reduces it in the samples row, right?
Oh, okay,
but
here.
when he
Okay.
gets the logits, then he has the 5, and then in the samples he only has 4, because he's squeezing the last in that to the last dimension, which is the channels.
Okay. Oh, I think this one is the probabilities. So since it's 2 colors, yeah, I think that's what I'll run through it. So when we ask for the samples, this will be KRC, and this will be the probability of 0 and 1. So this should be 2. So here I can show the architecture. So if we send in 1 2020, it will produce 2 2020. So we'll produce 2 numbers, probability for 0 and probability for 1. So logits are
so 102
okay.
KRC
I should
is that dimension.
It's missing. I can probably yeah. It's the 2 is this is the probability of 0 or 1, and then this is the sample. So this should be 100 by 2. Probs or logits should be 100 by 2. And then so if we look at it, it will be this isn't probability. It becomes probability after softmax, but this is the probability of 0, and this is the probability of that pixel being 1. I think 1 is black though, or 1 is white. Sorry, and so the first pixel is almost always white. Yep. Yeah, and I think that's the main difference between MADE and Pixel CNN, at least in this one, is that the mask has to be used in a CNN, and then we have a very much deeper network. Each one has to have its own mask, and here they've gone over, and so each. So going from this 64 by 20 to 20 to 64 by 20 to 20, they have 64 by 64 different masks of size 7 by 7, but they're all the same here. So in this one, they're all the same. Only in problem 3, this will come up that we could use different masks. Okay, and then yeah, the losses, it's just the cross entropy versus the one hot encoding, and the forward is almost the same. So yeah, for each layer, you just do the layer.out, and all of these are not relevant. So for us, but here. And so this is the output. So these are the 100 randomly sampled shapes. Okay, so let's go to part B. Which one was it? Oh, sorry, homework. Okay, part B. Here we have color shapes and MNIST, and we want to use independent color channels. So so the data here is so let me go to. So we look at the input data. It's now 3 by 20 by 20. Before it used to be 1 by 20 by 20, but now we have RGB. And the data is actually just only 4 levels. So or 3 levels, 3 or 4 levels. It should say here how many levels. 4 levels, so 0, 1, 2, 3. And we have 3 by 20 by 20. And so if we look at the architecture here, so I added this print model and then also the summary. And that this writes up this model, so it shows the full model, what the output shape is. But this one shows you the more in details about it. And there's also this one, the TensorBoard summary. So I have that also, but it wasn't as useful, so I haven't used it extensively. So let me see where I put the TensorBoard. The TensorBoard. So these are the different. Oh, sorry. To run TensorBoard first. Oh. TensorBoard logger is results, I think. Or runs, I forgot. I think it's runs. It's basically stores, TensorBoard stores in a folder. And so when you say write to it, it will write a file, and you can launch a web browser-based utility that you can view these things. So here's the Pixel CNN, and it's detailed, but it's kind of clunky to use. So we have input 128 3 by 20 by 20. That's our input, and it goes through the the mask convolution layer, and then the output is 20 by 2. So it's missing parts of it. It's 128 by 120 by 2. So it might be useful if you're looking at it. But this one also gives you similar information. So 120 by 20 by 20. And which just printing out the model doesn't give you that information. And I think it's because the code requires you to send the first batch of data here. And here it requires you to send first batch of data. So it actually runs the model once forward pass to get the actual data. So just printing the model just can't do that. So there's extra information needed. But yeah, sorry, that's diverting. But the point was that the input is 3 by 20 by 20. So that's 20 by 20 is the size, and then 3 is the RGB. And so the first one will convert the 3 by 20 by 20 into 120 by 20. And then it goes from 60 to 20 to 60 to 20 and 60 to 20. There's a really, really deep one. And then finally, the output is 12 by 20 by 20. So 12 because we have 3 channels and there are 4 possible colors for each channel. So there's 12 probabilities to choose from. And right, so before it was just 2 because we just have binary. So we choose 0 or 1 for each one. Now we have 4 levels for 3 colors. So we have 12 probabilities. But it has to be 3 different. We have to, when you do a softmax, we have to do the R first, G first, and the B next. So in 3 different collections. Okay, and all of this is a very, very deep network. And so they asked to use the res block. So the res block stands for, I think it stands for residual block, I believe. So when we add the residual block, there's a class here called res block. Yeah, here's the res block. And it's basically a stack of ReLU, Con2D, mask Con2D, which is our masked versions of it. ReLU, and it's just a stack of these. And note it goes, the first input is 1 by, it's a 1 by 1 convolution, which is, I believe it's just used to resample. So here we can see this first mask Con2D is used to change 120 to 60. And then the middle one uses the 7 by 7. So there's a lot of parameters here. And then this 7 by 7 with padding 3 is the one that we that we used in the previous one. That's where the masking occurs. And then there's another 1 by 1 convolution, which is again used for changing the 60 back to 120. And then it goes back again, and then goes back to 120, 160, back and forth, because they've stacked a whole bunch of it. And the name is residual block because it comes from the idea of skip connections. So residual block. I think they always give that this diagram. So you can come here and you can just skip over it if you don't like what's going on here. So that's the skip layer. Unfortunately, it doesn't show up in any of the here it doesn't show up anywhere, or even in the TensorBoard it doesn't show up. But in the code, this is the line. So here the output is the output of the layer, all of this, whole bunch of ReLUs added to the input itself. So just add these two together. And so in that way, there's the skip connection. So layer can go from like all these diagrams show, you can skip over all of these if you want by just making all the weights 0. But it's only achieved here by just adding it. So that's a little subtlety. Okay. Okay, so that's the difference. So the objective of the homework was to say, okay, that all color channels are independent. So, but how is it doing that? So what we can see here is that when we look at the model, we start with input. Let's say input is 2 by 3 by 20 by 20. I'll just put -1 here for the batch size. Oh, I use different notation. So this is our input. And as you can see, when there's RGB information here, but when we use the mask, the R doesn't know about the corresponding pixels. So so we have R, but the G doesn't know about the R, and the B doesn't know about the G. So they're three completely different independent channels. Right, when we mask it, we mask all three of them at the same time, all R, G, and B at the same time. So even though it gets mixed up here in the next layer, but we've masked all three of them out. So it's as if all three of them are the same pixel, and then we mask all three of them out. And so this satisfies the requirement, or that they're independent color channels. That the green doesn't know what the value of the red is. The blue doesn't know the value of green. So they're all three of them are completely independent.
So that basically means that there's no conditional, that if green doesn't depend on R and B doesn't depend on R and G, right?
Yep, yep.
So therefore you can mask each of them the same way.
Yep, yep. They're all masked exactly the same way, and I think it's because of the architecture, right? So here the input is 3. Or the input, I should go back here. The input is 3 by 20 by 20. So they're completely 3 independent channels, and there's 3 completely independent, 3 different masks, which will mask all RGB at the same time. So we'll process the whole 1 pixel at the same time.
Yep, got it. Okay.
Okay. So this, so obviously that, so following that, the next one is like, okay, make it so that the color channels are actually dependent on each other. So once you have red, you want the green to depend on the red, and then the blue to depend on both of them. So the I can just let it run, and then it's still going on, I guess. Okay. Yeah, and so with this one, they this is where the having lots of masks for each and every filter comes to play. When I first thought of this problem, I thought they would simple solution would be just to turn the so we have this input, right? So we could just say turn this into 60 by 20 image, and then move it back to 20 by 20, and then at the end do this, so that if we make it 60 by 20 image as the input, then each pixel depends on the one previous to it, right? So I thought this would be like the easiest, simplest way of doing it, but this is not the approach that they're taking. They're still using the they're still using this, but using the different masks, different masks to achieve this. So the input is still 3 by 20 by 20, but we're going to have different masks for different different usages.
It will be different masks for different channels, right? Because the R channel wouldn't depend on anything, or alternately, said differently, the G would be dependent not on B, but only on R. The B color channels would be allowed to depend on R and G, but not on itself, and so on.
Yep. So the only problem that occurs is that after the first layer they get mixed together, right? So this 120 by 20 by 20 has all three of them mixed together. So not only do we need to mask the first one, then we have to like mask all successive ones. Because the way convolution is, it takes the filter and passes through the image on all three layers and then sums them all up into one number, right? So in each number of the next one, so this one 120 by 20 by 20, each number has bits of all three channels in it. So that also needs a mask to say, okay, if I have this, shall I propagate it or not? Or
yeah,
right. So if this, so okay, it's probably better to just go to the code. Okay, so this was the results from the previous one. Yeah, and this is the color one. It only a few times it switches colors. So it shouldn't, because the original one doesn't switch colors, but yeah, it's pretty close. Okay, so let's go to the code 3C. So color conditioning, that's the name they give it. And so if we look at the mask when it gets here. Oh no, I forgot something. Okay, here's the code to create the mask. So if we're color conditioning, then there's an in channel divided by 3. So this 3 basically divides everything into 3 parts, like for the R, G, and B, right? So basically have to say, okay, we're dealing with the R stuff here, and then we're dealing with the G and the B. So each one has a slightly different mask. The caveat here is that so this is the first type. In the first type, in the previous one, here I'll go to this. So this was the type A, where the center one would not have a 1 in there, right? So it would just say, okay, it cannot depend on the current value. Otherwise, you would be cheating, because when we look over the first one, we can't have the first one already be in there. So that has to be masked out. But if we're doing green, then we need to say, okay, well, we're doing green, we'd like to have red. So in this mask, one of these are not, this is not zeroed out. So I believe it's, so you can go 20,
that
0.
both G and B shouldn't be zeroed out, right? Because you can use the R center value for G and B. Right? It's only R that needs to be masked out. G and B need not, because they can use the center value from R. Yep. Or more appropriately, G can use the center value from R, and B can use the center value from both R and G.
Yep. So if we look at the 50th one, so 0, 0 will say, don't use red, because you can't. But if we go to 50th one, which is, it's the architecture says we're going from 3 to 120. So it's 40 by 40 by 40 for RGB. So if we look at the 50th one, then we see that, yes, use red, it says, because we're doing the green one. So use the red one, right? And so if we look at the one, which is the green one, it will say, no, don't use the green one because we're doing with green. But then we look at the 91, it says, okay, use green because we're now doing blue. Right, so kind of like it's just the center one that matters. So if we go so we go back to 50, it's 0 because saying like, okay, we're processing the green values, so you can't use the green one. But if you go far enough into the blue one, so each one is 120. So the first 40 is red, the second to the 80 is green, and then the last one is blue. Then it will say, okay, now you can use it. So in that way, that's why they have a mask like this size, 128 by 3 by 7 by 7. So they have masks. In the previous problems, all the masks were same, but here the masks can be different. So they have a mask for every filter. And this is just for every layer also. So this is just for the first layer, right? So that on the second layer, which is of type B, there's a similar thing. Before, we would say, yeah, you can, the center point always is 1 if it's type B. But if we're color conditioning, then we kind of like, okay, is it, the third in, third out, all that stuff is the RGB. There's RG and B. So everything has to be multiples of 3. Otherwise, this wouldn't work. But yeah, so here you're saying, okay, is red coming? So can I use red? Then he says yes. If not, then it's left. So if this is doing
red can always be used, right, for type B, because
yep.
you don't care, and red is independent, the first channel, so you'd always use it. But then only G and B can get this additional, can only use the first third, not the.
Yep. So this one says use red for the first third in and the third out, but then leave the blue and green 0, right? Leave it as it is. So this will say only red is always 1, which is fine. This one will say, well, this one says red and blue is fine, but leave the green to be all zeroed. This one says, okay, everybody can use green. In the if we're using green, then the green can use all 3 values. Sorry, that can use both the red, green, and so
the blue can use RNG, right?
Oh, sorry, blue. Yeah, the blue can use all the previous ones. Green can use red and itself, and then red can use itself. So that's why they've divided into 3 pieces. And so I think it's more complicated. I don't know if it would work, just the one I said, like where we do 1 by 60 by 20, and then each successive pixel would depend on the one previous to it. So it's the same idea, and you just have to have 1 mask for everything. But
in that case, when you flatten it that way, how would you distinguish between the color dependencies of because you'd still need to do like the third as they are doing here, right?
Yeah.
Because you've just made you have kind of annihilated the dependency of the color channels if you make it 60 by 20.
Yeah, that's true. But since it's that could be the case that you have to keep the dimensions. I don't know if it would learn that it's RGB and it wouldn't matter, but there's
no. But the point is, it's not even that it just learns RGB. The fact is that you shouldn't let the G learn from the R if the colors are dependent. And in this, by doing 60, you would be violating it.
No,
That's the
no.
problem, right?
So it would be RGB, right? So each pixel would be so it would be 0, 0, RGB. So then we would first mask out R, and then the G would depend on the R, and then the B would depend on the all three of them. And the idea is that in the next one they squish it all into another completely 120 anyway. So even if it's moved here, the actual mathematics that's being done is the same. Actual multiplication that's being done is the same, because all you're doing is changing the dimensions of it, but the actual values that goes into 120, 20 by 20 is the same, right? Because even though it's here or here, it's still being applied the same way. Or maybe that's assumption, that's not right, but because either way it has to go into the same number. So, but the order might be different, so it could transpose it, the orders. But then, yeah, I'm not sure, but that was one thing, was if it would work or not. But it would simplify things, but I don't know if it would be better or not. Maybe something to try out in this. But yeah, that's the only difference between this and part B and part C. That's the only difference here. And that solves the problem of autoregressive color channels. Okay, and so let's go to part 4. Conditional.
Sorry, before we go there, what do the results for this one look like in our? Can we just look at that, like how they are different from?
Oh, okay.
The what do the results look like?
That's a good idea. This is the one they produced. Just still learning, I think. It's still going through epoch 1.
Yeah, can we look at?
Okay, we'll look at this one. This one seems to be all pink, whereas the other one actually had different colors. So here, this is the one, sorry. So here there's no multiple colors, right? So all of them are solid colors.
Yeah, hard to tell because we're not comparing apples and apples. So in this case, it's shapes. The other one is numbers. And
yeah.
Like you said, block colors.
Yeah, it's solid colors. I was looking at the MNIST data, not the but here here's the results. No, not yet. It's still epoch 7.
Okay, we can move and come back when it's
okay. Yeah, so and I think we can compare it really quickly. Yeah, this one is the one from before. They also had solid ones. Yeah, right here, this is the 2 colored ones where it switches colors. I had some more like here, the color switches, but this one doesn't. So maybe that's an advantage here, that I don't see any color switches. Yeah, all of these errors, I think this is the training error. They all, so the final loss is 0.236, and the final loss is 0.444. I don't know if we can say, well, from this number we did a better job than the previous one. the test loss. If we can use that to compare the quality of the algorithms. But yeah, this is the results, I believe, or no, one more epoch. But okay, we can move on to this one. Conditional pixel CNNs. In this one, the problem is to do this to generate circles or squares or stars or triangles explicitly. So rather than just say, just give me 100 of whatever you want, you say, I want 25 circles, 25 squares. You can give a label and it will generate a sample of that label for you. Right, so this is the results from the run here on this computer. Yeah, it does have some artifacts here. So anyway, so this is the new problem is that we give a label saying I want you to generate something of this class, and fortunately this is a label data set, so this one actually knows what shape it is, so we can use that. And the trick here is to just add it right here, this part. Oh, it can't be highlighted, but we have the weight and the bias, and then we just add a y. Y is our result. This is the one hot encoded, and you just add it to our convolution. So if we look at the code, part
Sorry,
D.
could you go back to that where it says broadcast spatially and added channel wise? So that means it's broadcast to all the HW, height and width, and then added.
Yeah, I believe this.
Every channel.
Yep. I think it's just like the bias. It's broadcast. The shapes are slightly smaller, so when you do the convolution, the shape is different. But we can take a look at the shapes. I think this Y is a one hot encoded. So it's the 0/4, like so 4 vector, and then we have a V matrix, a linear neural network that will just move it to the right shape, and then it's broadcast over everything. You can just take a look at the code here. So this is the one. This is the pixel CNN, and this is, we're not using the residual block, so this is the Con 2D. And so yeah, so there's a lot of like convoluted code. So conditional size conditional size is a flag. So you have to just differentiate from color conditioning. Color conditioning is the one that we did previously. So conditional size is just the size that we give right here. Sorry, it's jumping back and forth, but conditional size is the number of classes that's available. And so no, this one didn't work.
So here we have gone back to binary. Is that why it's 2, then conditional 1 HW, then 2?
Yep, it's back to binary. So this is, yep. No, it's binary, just 2 levels, 0 or 1, and this is only one color channel. And so the input data again is train data is again back to 1 by 20 by 20. And so that's the shape, and then each has 2. And so if we look at the output, okay, doesn't show the output here, but the the output is the same. It's 2 by 20 by 20. So you have probability of 0 and 1. Somehow this training shape, this doesn't work because you have to give some training data, and then the shape doesn't matter because it has some of the data is kind of the labels are also added in there. So I didn't have time to debug it to go into detail on how to fix it. But yeah, so the difference here is we also have the labels now. Not only we have the data, but we have the labels, and there's four different types, right? Circles, squares, star, and triangles. So the labels are also there. So what we do is we say, okay, so where is it here? So we give the conditional size as a number of classes, and the number of classes is obviously 4 here. So this way we have like a very, very complicated way of saying that, okay, we are going to we're going to add the conditions into the neural network. So when we do pixel CNN, conditional size is greater than 1. So this conditional size, and then this affects this right here. And if length is equal to 1, in our case it's 1. So I think this is for the optional grayscale CNN. It doesn't do anything here. So if it's grayscale, it has to do some other stuff. And so the conditional then is also how it uses the condition is that when you do a forward pass, it expects you to send data. Oh yeah, I think I did this to fix the. This is to fix this. I think it works. Yeah, it does work. Okay. So you can see the output is 2 by 20 by 20. Yeah, but if we look at it here, there are these linear ones that are different from the previous ones. The previous ones didn't have a linear block. So where did this come from? So this one is okay. So in the forward pass, so we get X, right? And condition is actually the labels Y, but it's one hot encoded like this one. So this one would say these are both triangles. So we send the condition, and this would go in the layer, which is the MassCon 2D. So that's where it gets used. So here's the condition. Says condition if blah, blah, blah. If we're using condition and it's size 1, you do something called condition operation. And if it's ours, we just do a linear. So that's where the linear comes from. So what it does is it takes a number, a vector of 4, and turns it into a value of 64 values. And it's in every layer. So this condition has to be added to every layer or every CNN. So we'll take that, make it size 64, and this is broadcast over each and every pixel here. Right, so, and this is done for each and every layer. So this linear layer, this linear, all of them get the same value. So I can see if I can break here.
So this is the part where they say it's broadcast over H and W and then added in per channel. That's what we are doing here.
Yeah. Yeah. So because you can see the linear changes it to 64, right? The input is of size. Oh, I should redo this here. It will.
So 64 would probably do it per channel, and then the broadcast happens over the 20 by 20.
Yeah, the broadcast happens over all the pixels, and if there are more than one channels, it will also be broadcast over the channels.
Yeah, but by making the linear, we've already converted it to the number of channels, right? Because that's what the linear layer is doing. Taking 4, pushing it to the number of channels, whatever happens to be 64 here, and then broadcast over the 20 by 20.
Yeah, I think they call the 64 something else. 64 is called something else. I don't know if it's called channels. The channel is for like RGB, but or maybe.
But yeah, I meant the number of filters.
Yeah,
right?
the filters.
They,
sorry. Yeah, you're right.
Yeah.
It's filters. Yep. So the this one is 64 by 1 by 1, and then it's broadcast over the output, which is 64 by 20 by 20, and it's done for each and every layer, and it's added everywhere. So that's the only change. The only other thing that I see the condition do is layer norm. So they change the shape. So instead of being contiguous, they say, well, we got to put it back. And then I think the layer normalization will actually normalize over over the right values. It has to be the right shape. So all it is doing here is changing the shape. So the normalization doesn't. Oh no, sorry. This is for color conditioning, not for this. So there's no condition here. So never mind. I should have mentioned this in the color conditioning part. The layer normalization does that. But yeah, that's the only part that does it is the mask conduit. When it does a forward pass, it asks the linear one to also multiply it and broadcast it and add it over everything, and that's the only place. The residual block also does it, but I mean we see it here, but it's just sending it to the to the convolution block. So all of this is just passing it around, but yeah, all of this is just, yeah, none of it actually does anything with it. So everything happens right here. And this is a linear operation. Okay, so that's the main idea. So of this, and when we sample it, I think that's the other interesting part is when we sample it, we send a condition, and this is done here. So we can. It's going to train, I think. But here, what they're doing is they're making 100 samples, but 25 is of each of the classes. So if it ever gets here, it will just show that the one-hot encoding is similar, but there's 100 of them, 25 of a square, 25 of circle, 25 of. Oh, here we go. I think we got it. So if you look at one-hot, we'll just see, yeah, it's 25 squares, 25 this, 25 that, and so we say, okay, sample, but here's the condition, and then all it does, it sends it, sends it to the feed forward, and then when it calculates the probabilities, it takes into consideration the conditions. And so then it's the same again, multinomial distribution. And as we can see, the first 25 are circles, kind of circles. The next 25 are squares, and then the next 25 are stars, and then the next 25 are triangles. Okay, I think this concludes question number 3. And they're bonus questions. I didn't look into it much, and this is also covered in the collab, so we can look into it a little bit more there. Okay, is any questions, or should I go to collab next?
No, let's go to the collab part then.
Okay, yeah, I have the notebook here loaded in my so it's not as much useful as going over the using the web-based one, but it's a little bit useful sometimes. So we'll just go over it quickly so we can just have a good idea of what's going on. I think we've already done this one in the first one. So this is the picture of the distributions.
Yeah, in interest of time, maybe we can skip what we have done in the homework and just look at, I was thinking of the collab, there's a lot, I jotted down about 10 or 11 different things they cover. And one suggestion I have is maybe we should focus on, there is RNN, but given what he said about, RNNs aren't that useful, or maybe we skip that and look at the different orderings of made is one that I believe the collab covers. I just made some notes here. Let me rattle them off. Then the Wavenet implementation is covered, which would be interesting. We haven't seen that in the homework. So there's different ordering with made, which would be interesting to look at. And there is Wavenet. Then there's same, maybe comparing the receptive fields and how there's no blind spot, but that's also covered elsewhere. So that may not be that useful, but made, Wavenet, and then self-attention autoregressive model. And that would be interesting to look at the code of how attention in autoregressive sense is implemented, or how they have at least implemented it. And then the speed up techniques. There's an image super resolution implementation they've shared. And then the 2 speed up techniques they touch on in the lecture, which is hierarchy and fast sampling. So I thought those 6, and I'll kind of post those in Slack, but those 6, if we cover in 1 or 2 sessions, just look at the code for that, that will be helpful, because these are the things we have looked at in great detail in the homework, and we can go back and listen to you, Merchant, going over that. Okay.
Sure. So let's skip over this. This one is sometimes not met. Okay. Different autoregressive model architectures. So this is the RNN one. So one of the problem I noticed with the collab notebook is that so this right here is underlined. So this is dead code. So this actually is never used anywhere. RNN. So so all of this actually is not used. So if we look at how they do it, they load the pre-trained models, and so we have a whole bunch of these models that are already pre-trained, and then they can just use the model. So none of this is actually being used. So this is just like code that doesn't actually get used when we run the collab notebook. But the models are already there. So I think it's to save time for people, but then it is kind of like you can't really see what's going on. You can see, okay, well, I want to see the sample of the model, and you can see this is RNN sample, and you can kind of see what's going on. but you can't see the training part of it and can't debug into it because already load a pre-trained model, which is fast, but at the same time it's a little bit hard to do. But anyway, so what they do here is, so they have the results, they have different models loaded for epoch 0, epoch 1, epoch 2, and epoch so on. And then each of them are, oh, this is initialization, this is all random, and this is epoch 1, sorry, the one below. So, and then they show the different results for different epochs of training.
One particular thing maybe we can spend a little bit of time looking at in this code is, and there was a question asked some time back, is how they add the location. So if maybe we can just look at that portion of the code where somehow they would have added the location of the pixel into the RNN.
Oh, okay.
So the
yeah.
second implementation, yeah, this one, RNN with pixel location appended. So it'd be interesting to see how they do that.
Yeah, it's the same problem. It's like it's loading it from the file.
Yeah, no, not by running it maybe, but just at least looking at the code. I mean, which is not as great, but still would be interesting to at least look at the code to see how they have accomplished it.
Okay. Yeah, I'm not sure how they're adding it.
There's this append lock, and how do they, much like the conditional.
Yeah, this one.
How they, yeah.
But this one doesn't go anywhere. So append location doesn't work. So let me try this. And maybe they have fixed it here, append location. This one here.
Yeah, what did they do there?
Yep, they seem to have concatenated it at the end. So I'm not. Go ahead.
Sorry. So if they seem to find a range of 28 and then make it convert it to a mesh grid of 28 by 28, and then I guess we need to take that code out and print it. But then they seem to permute, and the contiguous is just one, and then unsqueeze the second channel and then repeat that, or should be 0111. The magic seems to be in converting it to a mesh grid, and then.
And I think they're concatenating instead of broadcasting and adding it everywhere like they did with the in the previous one, class conditional. They seem to just add it to the end of something. But as I was, yeah, I'm not sure. I don't know much about RNN, so maybe this is something that's RNN specific.
Yeah, so it's just a matter of sending. They've just concatenated the locations. Yeah, well, I'm trying to figure out what's the dimension of the locations that they provide, but it's some dimension value, meaning some values that they append or concatenate to the X input. And
I think it's.
I guess the magic. Go ahead.
Oh, it's MNIST, so it's 28 by 28. That's probably why it's
right. Yeah, no, that I got, but the magic seems to happen. The mesh grid is just converting it to 1, 2, 3, 4, 27, same thing on the X and Y. So it's just creating the coordinates for each of the pixels is what the mesh grid stuff is doing.
Yeah,
right. It's just converting the, creating a X by Y mesh grid. The only thing I can't figure out in my head yet is what the third line is doing, which is permuting it and then unsqueezing and then repeat the shape. That's the part I haven't yet got. But I guess once we figure that out, then basically that just gets concatenated with X to provide the location of each pixel in a 28 by 28, which obviously it'll be like 0, 27, 127, or yeah, 0, 27, 127, 227, all the way up to 27, 27, right? Because that, or 0, 27 for the last pixel on the 0th row, and then we go down. So that's what the mesh grid is doing. But what the third line is doing is something that I can't figure out in my head. Maybe somebody can talk to. But anyway, that's the way, I guess. They seem to be concatenating the locations, as you said, with X. So that's the way they are adding the locations to every point of X. That is, every pixel also gets the location concatenated with it.
Yep. I think this would be a good maybe next exercise next time is to actually have it go through the model and not just load it and see if we can replicate it. Okay, this is the one that had pixel values appended as features. So yeah, it can load the values and just show the the pixels, and it's pretty good. And then we have made. We already went through this in great detail, so we can skip this. This is Wavenet. Let me go to Wavenet. So Wavenet, I printed out the model here, and I wasn't quite sure. Here's Wavenet. So I think we all remember the example, right? So that you have a new one, and then the previous one, there's a dilation in the past, and then the most frequent ones are used more often. This diagram. So see if I could figure it out, but it doesn't seem like it's quite obvious what's going on to me. So again, this is another one that I think we have to run through and look at the training and see what is going on in detail. But as you can see, everything is 1D convolution because of the wave is designed for sound.
I think in this case, since it's 1D, it's simpler, but at the same time, I guess the magic is usually in the dilated causal convolution 1D as opposed to the mass. So it'd be interesting to look at what that does.
These terms are, I think, specific to that implementation here.
Right. But
so
that's what I mean, like looking at what the dilated causal convolution 1D code looks like.
And they also have this is the one. So this would also, we'd have to look through it a little bit more. Also here, I think there's a encode. This is the actual code from it, and it says it's from this GitHub page. And the dilated and causal, all these are not residual, are not used in the paper. So it's and even the type A and type B are not used. So it's specific to this implementation. But I was going to see if there's a pen lock. Okay, where did it come from? Pen location. I think it's the same as before. Yeah. So they use the same technique of appending the location, both in Wavenet and Pixel RNN. Okay, and so then we have Pixel CNN, which we've already gone in much detail. I think it's the same code as from homework. Yeah, this one is kind of interesting, comparing the receptive fields. Because if we look at this, so this is pixel CNN, this is, okay. So if we run this code, it'll actually show us the blind spot. As you can see, this is the current location, and it shows all the blind spot. And if we look at the plot receptive field code, so what it's basically doing is it takes a position and does a backward, and then they calculate where the gradient, when we do a back propagation, which gradients are actually have changed. They're not zero. They actually got affected, and so so whichever ones are affected are set as 1. And so that's why we can see, like, when we did this, these are all the ones that back propagation could get to, but all of these, the rest couldn't get to it. So in the first, I think in the first layer, 2 layers, it can't get to most of them. In the second layer, it can get to most of them. After 5 layers, it can get to this position, it can get to all these different ones, the receptive fields, but it can't get to any of these ones. So that's a cool way of
blind spot, right?
Yeah, that's the blind spot, and it's a cool.
So no matter what happens with the way of just the convolutional network and the masking, the effect is to create a blind spot as we move. And the blind spot, for example, for the pixel, if that green pixel were to be at the left corner, you'd see a stack going up diagonally from there. Right.
Yeah, I think we can even plot it. We're doing 2, 3, 5 and layers in 2 layers, 3 layers. Okay, I guess we can't. This is probably the layer. So this is 5 by 5, and let's see, 5 by 5 displaced, right? So let's say 8 by 0. And if we run it, oh. Okay, it's still drawing it over there. I probably should put it there, but that's the blind spot. But all of this is the blind spot here. It's still drawing it over there because sorry, this one, it should be 80 also. Yep. So we can add 7. We can add 7 to it. So after 7 layers, yeah. But this part is still like, no matter what we do, the back propagation cannot affect any of this.
Yeah, so that's really bad, because you can pretty much see very significant hole.
Yeah. So yeah, and so they have this one, the pixel CNN with horizontal. So this was one of the homework exercises, optional ones, I believe. The gated ones. Yeah, gated pixel CNN is to use a horizontal and a vertical one. So it's another, is to use a different one. And this is, oh, I should do 7 also. So this kind of fixes the problem here. The blind spot is, I mean, if we do more, I think it will be covered up. So let's say, so after 11, almost everything is covered up. So there's no blind spot. And yeah, and so this is the, so they have the horizontal vertical stack pixel CNN. So they have 2 different masks. There's a horizontal and a vertical mask. So this is given in the homework. Okay.
Yeah, and the way they combine it is also important and interesting. I think the tutorials that I've pointed to kind of take you through the implementation pretty well. So I think that would be very interested. That covers it in detail, how to combine, because that's the, I forget now in the terminology, but that's the CNN++ maybe and stuff, like where you bring in the vertical and horizontal, and the vertical feeds into the horizontal, but the horizontal doesn't feed back into the vertical.
Mm-hmm. And so I'll keep moving on. So we have the self-attention autoregressive model, and yep, they have all this stuff here about the multi-head attention, blah, blah, blah. And what they do here is they just say, well, your model is just a transformer. And so if this is the transformer from their repo, and I think there's the multi-head somewhere. I guess there's the decoder layer. So they have a slightly different implementation of the multi-head attention that they're using. Well, I guess this is the multi-head attention they're using then. But so when I print out the model, it uses 2 stacks of decoders. So they have a mode called pixel location, which is not, they have different types of transformers. So there's stacks of 2. So there's a linear one, which probably is to get into the right shape. And then there's a decoder layer, and then another decoder layer. There's 2 layers. And then there's a linear one that probably puts it back into the right shape. So I have some pages about transformers. Yeah, this is the original transformer picture, right? So the left one is called the encoder, left part is called encoder, and the right part is called the decoder. And then, so we have N is 2 here. We have 2 of these. We have 2 of these encoders and decoder. We have 2 of these decoders, and we're not using any of the encoders. And I think this is the same idea as GPT-2 or the image transformer, right? So they just have stacks and stacks of decoders, and then they send the image through here. Or I should go to the actual paper here. I read this a long time ago. Yeah, so they take the picture, they cut it into small boxes, and then the patches are sent through. This is the image transformer, vision transformer paper. So you take the image, you cut it into small pieces, and then it goes through just the decoder part of it. And there's the multi-head attention, and then the normalization, the MLP, and then goes 2 times. So maybe the same one here. So there's the linear layer, or that just gets the right shape, and then the multi-head attention, and this is the stuff inside multi-head attention. There's the linear layer, the MLP. There's a norm somewhere. I guess they have dropout and layer norm. So it's slightly different, but maybe this is the position feed.
Do they do the position feed? Is it similar, or is the position feed different for the transform? Can we look at that for a minute?
Oh, okay. Yeah, they do talk about the autoregressive orderings. See if the chance. I believe they. Yeah, the position is added here in the paper. They always also say how they added it. Oh, there. They just add the position here. Patch position.
Right.
Embedding.
No, in the.
Okay.
In this implementation, have they, like, what do they do with the pause encoding?
positional encoding here. And it's a module. Oh yeah, it's that sinusite thing that the.
Oh, so it's the same. So they use the same thing as the transformer. So they actually encode based on this sine cosine wave
Yeah,
thing
looks
that the
like,
original transformer does.
I think so.
Yeah, that's what is done in the transformer paper. So they use the, okay, interesting. So they use the same thing as what the original transformer paper did.
Yep.
And they combine it with value. They probably do the, here's a thought, and maybe we can all look at the detail offline and discuss it next time. Is it looks like the two decoders might be because of the it may just be implementing the vertical and horizontal stack, or combining all the pixels that matter for the vertical in one part and then sending it to the other. But I might be wrong too. So that would be interesting of why they use and what and how the two are different. The two decoder, whether it's exactly the same or different values are fed into each one.
Actually, wait, actually a second. They said mode equals pixel location. If mode is pixel location, then input size is 3. They're doing something else here, looks like. That's just, it's being, I don't know, because position encoding would be the mode, but I think it's the pixel encoding mode, so they're not using this. Yeah, I think it would be.
Look at where they're calling it, or in the code, like is it pixel location or encoding?
Oh, yeah, it's pixel location. Sorry. Yeah.
Oh, okay. So they are using pixel location. Interesting.
Yeah, all here
location,
sorry, go ahead.
So the pixel location, what did they do? They just gave it. They just said input size is 3. That's it.
So yeah, I think it would make sense to try and maybe next time try to actually train this model, transformer model, and see what it's actually doing.
Because I think if we can just spend, maybe the next time just a little more on the transformer model, maybe the Wavenet, because that's something again we haven't looked at before, and then just look at the image super resolution, the hierarchy and fast sampling code, and see what's being done in those. And I think that should not take us maybe even the full 2 hours, but that's fine. I mean, we have gone full 2 hours in multiple sessions. So maybe given what we've gone through, I'm okay if we stop here and then use the next session. Because after that, we'll have a break for 4th of July. I think we have 1 more week before that, right?
Okay. Yeah.
Next week is the
27th. Yeah.
7th. Yeah. So we can have that and then finish up.
Oh, just 2 from the doctor. Need to take 2 more. Sorry? After that. I got to get 2 more. A B.
Parents?
A D. Oops, sorry.
Oh, okay. Yeah, if we have a little bit more time, 20 minutes, I can just go through the rest of the collab, and we can just kind of discuss it.
Okay, yeah, maybe we can do that and then stop whenever we have 20 more minutes, but we can stop a few minutes before get through as much.
Okay, yeah, it would be good if with the implementation, I might need help. So I'll probably ask people if they can help, if people are interested in training these models. And yeah, okay. So they have different autoregressive orderings, but this is made on MNIST. So we can skip it. I think we don't know if we talked about
that one we did talk about it, but again, we didn't. I don't think we saw an implementation. So again, I'm curious as to, is there any difference in the implementation, or I thought our implementation allowed for the different ordering anyway, right? So what is it that is different in the made with different ordering?
Oh, I think what they're doing is the sequence is not 1, 2, 3, 4 like left and right, but they're just experimenting with different orderings. Like, let's just make a random permutation of all the 784, and will it still learn it? Is there some sort of spatial ordering that it's preserving? So here it's just random, right? Permutation of 784, just whatever, the ordering is random. And then this is the loss, 0.1. And if we do even and odd, so here it is, A range 7842. This is the even first and the odd. It actually is worse. But it looks better, I think, but the loss is worse. And so raster scan, this is the one that we were doing, raster scan left to right. And actually it's even worse loss, test loss, but looks much better. Columns, this one is even worse. So we go, 28 by 28 reshape, yeah. But we're going column wise down instead of raster scan. Top to middle and then bottom to middle. So that's another one. Ordering. Okay, and I think this is kind of inspired by the question that someone said, that instead of raster scan, we actually follow the ordering of the pen, right? Like, what if we go left to right? Or maybe that's what it was. So this is the conditional autoregressive models. I think this is adding the condition to the transformer.
Yeah, this is what you took us through, right? That
yep.
The labels are provided.
And so this is the pixel CNN. We've already been through this, and this one was broken. Yeah, I didn't understand what this was supposed to be, because this is part 2 of
sorry, one question.
Sure.
They seem to have different variants. There's a conditional, and then there is a class conditional. So what does the conditional do? Is it just conditional on color, or is it, because we saw they're two different, right? One is conditional on the color and the other is class conditioning on the class. But what does this just conditional mean?
I think they mean class conditional.
Because there is a class conditional separately after this.
Yep, they just use the variable called color conditional, but then I don't think they use the word color conditional in the homework anywhere. So here it's just in the code they call it color conditional, but it's just autoregressive color channels. But there's nothing dependent. There's no conditional term. I think it's just in the code they use the term conditional. But it's just different color channels. I think when they mean conditional, I think they always mean class conditional. So here it's conditional pixel CNNs, and it's always class conditional. Okay, and so this is the a pixel CNN. We already went through this. Oh yeah, image super resolution. I merely missed it. So this is pixel CNN, but I think the way they do it here is you take the image, you downsample it, and then put it through the sample again to see if we can reconstruct the original image, if it can do the super resolution. So I should look at the actual. Oh, I've lost where it is. Maybe here. Yep, here. This is super resolution. That code doesn't work in the notebooks. I have to debug it. But basically, you take 3, and then you use the interpolate to make it into a very blocky. You pixelate it, and then you pass it through pixel CNN and see what happens as a sample, and see if it fixes it or not. But use this as a conditional.
When you say this, you mean not the label, but the output generated by the chunky. When you say chunky, did they reduce? So they scale it, I guess, in X and Y. So the number of pixels fed into that is smaller by a factor of 4.
Yep.
Or in this case, by a factor of 16.
Yep. And I think the conditional here is not the class label, but like the lower resolution. Because conditional here is the interpolation of this. So I think that's the class conditional. So this would be also a different kind of conditional, right? So that's why it's under the conditional. This is class conditional, and then image super resolution is also under conditional. So this is another, I don't know, it didn't work for me, but I don't know if we can go to this model.sample. Yeah, it's still doing that. So I'm not sure what's going on.
So
they changed it to.
So maybe this conditional is the conditional that I'll look at the difference between, because they give a class conditional implementation in Colab, and then there's a conditional before that. So I'm still puzzled why they have 2 of them if they are both the same. So I'll look at that to see whether conditional implementation they have allows you to condition on a prior image, which wouldn't be the label, right? It would be full image at a lower resolution.
So I think what I thought was that it doesn't really matter. The actual neural network, the linear part, the conditional op, will oh, here they have a completely different thing here. Okay, I thought it wouldn't matter, but they do have a.
See, here they would have to scale the image, because in that case, all they are doing when you're conditioning on just the label is just converting the label to the number of filters and then broadcasting it over H and W. That's all you have to do for label conditioning. Whereas if you're conditioning on a full image, then you have to do this kind of stuff where you are probably scaling it. But we can look at this code and discuss it next time.
Okay.
What is actually being done here, because in fact, if you see they are upsampling it back probably to, and a factor of 2. So that's probably bringing the image back to the full dimension that you subsampled from. So you have to bring it back, and that's the conditional. That's probably the conditioning that's happening, and therefore they have a a conditional autoregressive model, which probably that implementation allows you potentially to do this. Anyway, that's something we can look at in and discuss whether our understanding is correct next week. So we can start there.
Okay.
Possibly.
Yeah, that's a whole another thing I didn't look at. Yeah, and so there's some more things. Yeah, this one I didn't really understand what use in homework. It said not this one. Okay, sorry. This one. So gated pixel CNN is the one that you remove the blind spot from. Grayscale pixel CNN, it says train a grayscale on colored MNIST. So I'm not sure what they mean by this. So but so I'll just skip this for the time being. Maybe someone has an idea of it, they can explain. But besides that, there's the parallel pixel CNNs.
Oh, sorry, the hierarchy as well. Again, I invite anybody to take a look, see if they can explain, but superficially, and I haven't looked at the code, but recalling from the lecture, it may just be that, he took two examples or two methods by which you could speed up the whole process, right, of generating these, and especially during inference. And one of them was this fast sampling, but the other one is the hierarchy where he said, just assume for a minute that you can divide up the image into some blocks or hierarchy and assume that a pixel doesn't depend on everything else, but some chunk of the image, and then build it up hierarchically, and that would enable you to speed up the inference much faster than if you were to assume everything is dependent on every pixel from the past. That's my recollection. I'm obviously doing a poor job of what is, but that portion of the lecture is probably what is implemented in the demo, is my thought, but I could be wrong too. So it'd be interesting to see whether that's what they do and whether it's for speeding up. Because he talked about two ways of speeding up inference. One is this fast sampling, and the other is hierarchy that I recall from the lecture.
Okay.
But it will be interesting to see the code and see whether I'm just rambling or it's relevant.
Yeah, this is actually in the homework. So I think this code actually runs. Oh, sorry, this is actually in the homework. So this code should actually run, and so should be functional. Yeah, and this is the parallel pixel CNN paper, which and I didn't look at the code of it, but basically what they're suggesting is that instead of doing pixel by pixel, you do make regions, and you assume that there's dependence like these, but one and one.
So this one covers what I was talking about. So maybe the hierarchy is something else.
This is the parallel multi-scale where you have different scale of things. So you can split it and merge it back, and so this block is not dependent on this set of pixels, like maybe this, but I don't know how you chop it up or do things like that. So those are extra credit ones and also part of the demo. So yeah, so this is the full collab. I think we're almost out of time also, but what I wanted to say was I think a whole bunch of these are like interesting implementation exercises. So what I can do is I can just first make a starter GitHub repo that then hopefully people can have time to help me out or finish it and do the presentation on each of these interesting ones. Like as you said, super resolution can be one. All of these can be other ones. And all of these.
I mean, we can try whatever and at least discuss next week. So we'll have one more week on this, and then after the July 4th, we'll start on the flow.
Okay.
So that would be a good break. So next week we can just discuss if we
Okay.
haven't made much progress, that's fine. But whatever we, Wavenet, then the hierarchy one, the self-attention as to why multiple decoders are needed and what they do differently and whether it's identical, image super resolution. I mean, we'll obviously not have time to get to the implementation of all of those, but just at least a better understanding of what each of them does and
Okay.
doesn't do, and the relevant portions of the code, like, even on the lock thing, I'd like to try out maybe what the lock stuff does with MS so we can understand how to provide the location stuff.
Sure.
So bits and pieces of that kind that might be interesting is what, and if there isn't much, and we can wrap up early. But I think that would be a good call for next week, and that should wrap up
Okay.
the whole first.
Yeah, and if anyone's interested, yeah, I'll make I'll make the autoregressive like starter code and see if we can fill it out, and it should be trivial. It shouldn't be that much, but at least it will just it'll just be going through and making sure everything's all right. Yeah, I'll post the GitHub links.
Great, thanks a lot,
Okay.
Mohsin. Thanks for taking us to another 2 hours.
Okay, no problem. So it should be next week, and we should be we should be back to the lectures. Yeah, spend a lot of time on module 2 or this part. So where is
so
it?
we can wrap up next week, and then
Yeah.
after the July 4th week, we can get into the flow models.
Okay, that sounds good. Yeah, hopefully it hasn't been too like a slog through this.
No, but actually, if we don't go through the code, then it's like they talk about the illusion of understanding, and I think that's what happens is we think we understand, and then as soon as we have to implement, then all kinds of questions come into play. So I think going through the code, at least in my opinion, is where the rubber meets the road of do we really understand it. So I think it's a slog, but it's a worthwhile slog, I feel.
Okay, and I was gonna say I saw this paper some time ago, MLP mixer. Basically, they're saying that this achieves better performance. It's just an MLP, multi-layer perceptron, but it achieves better performance than CNN. So this was by DeepMind or something like that. I forgot. Maybe this is DeepMind. But if anyone's interested to like try to make an autoregressive version, it's Google AI thing, Google, to add, see if we can add and discuss an autoregressive thing on this MLP mixer thing, because this is all label data set, I believe. So yeah, ImageNet stuff. So that's also another option. So could be a fun project to do, or something to have discussions on. So,
yeah, great. If you can post the link.
Okay, sure. I'll post the link. Yep. Okay, great. So thank you, everyone.
Great. Thanks a lot,
Yes,
Mohsin.
thank
We'll
you.
have one more week and wrap it up.
Okay, we'll talk to you next week.
Yeah.
See you guys next
Bye.
week. Thank you.
See you. Thank you.